Welcome to this session of the course. So, in this class what we will be looking into will be categorizing the various. So, in the last class we have seen how a membrane is cast and what are the various controlling factors of to control the pore size distribution of the membrane. Now, in this class we will be basically broadly doing the categorization of the membrane based processes. First, we will divide the membrane based process into two broad categories. One is the symmetric or homogeneous membranes, and another is the asymmetric membranes. In symmetric membranes, throughout the whole cross section of the membrane, the pore size distribution is more or less uniform. So, it is more or less uniform pore size distribution across the cross section. But in case of asymmetric membranes, there will be a distribution of pore size distribution is not uniform. Is not uniform across the cross section. So, in case of asymmetric membrane, there is a thin skin followed by a porous substructure, and typically this is a dense thin skin, and there is a porous substructure which will be following the thin skin, and the controlling the selectivity of the membrane will be coming from this thin skin. And what is the objective of this porous support? The porous support will be giving a kind of porous substructure will be giving a kind of mechanical support to the thin skin, and typically this skin will be having a thickness between, let us say, 10 to 50 micron, and the porous substructure will be rest among the total thickness of, let us say, 150 or 200 micron. So, because the actual membrane is this thin skin, the throughput of the process will be really very high compared to a homogeneous or symmetric membrane. In case of symmetric membrane, the pore size distribution is more or less uniform throughout the membrane. So, therefore, there are two disadvantages of this. One is the thickness of the membrane is really very high, that will be decreasing the throughput of the process, but if you have a dense porous structure, the throughput will be always less. So, for example, a symmetric or homogeneous membrane is a kind of reverse osmosis membrane. On the other hand, the typical other membranes like all grades of ultrafiltration, microfiltration, they are typically asymmetric membranes, and because of the smaller thickness of the skin, the throughput of the process is more. So, let us look into the various types of motions. Those will be occurring in the membranes. The first type of motion or transport mechanism is permeation. Permeation is a process involving three steps: dissolution, diffusion, and desorption. So, first the solute will be dissolved into the polymer matrix, then because of the concentration gradient, it will diffuse from the retentate stream or the feed stream to the permeate stream, and then it will be dissolved in the permeate stream. So, these three mechanisms in one is called permeation. Then comes Knudsen diffusion, if d by lambda, d is the pore diameter and lambda is the mean free path, is less than 0.2, then the diffusion is called the Knudsen diffusion, typically for the diffusion of gaseous streams. Knudsen diffusion becomes very important. In case of reverse osmosis, the permeation is very important, and then the third transport mechanism is convection. So, convection is basically occurred due to the pressure drop, pressure gradient. There can be a mixture of convection and diffusion as well, and this type of transport mechanism is observed in ultrafiltration, microfiltration, and higher cutoff membranes and more porous membrane. Once we understand the different transport mechanisms, those are involved in the membrane based processes. Now, let us categorize these processes broadly. So, and in detailed. So, detailed categorization we do. There are mainly 4 processes we will be dealing with. One is reverse osmosis, and there is ultrafiltration, reverse osmosis, then in between reverse osmosis and ultrafiltration there is nanofiltration. So, reverse osmosis, nanofiltration, ultrafiltration and microfiltration. So, let us go and see the characteristic of each of these processes in detail. In case of reverse osmosis, typically we are talking about separation of monovalent salt. Salt like NaCl. So, this is widely used for the desalination to produce the potable water from saline water, so sea water. So, a good reverse osmosis membrane means we are definitely talking about 95%, more than 95% separation or rejection of sodium chloride. Okay. And typically the pore size is varying from 2 to 10 angstrom. That is a typical range of pore size in a reverse osmosis membrane. Osmotic pressure plays a very important role. In case of reverse osmosis, we will be coming to the concept of osmotic pressure definition and other quantifications probably later on in this class itself, and then we will be seeing why this osmotic pressure is important in case of reverse osmosis. So, osmotic pressure plays a very important role, and the transport mechanism is permeation, because we are talking of a very small pore sized membrane. It is a dense membrane, something it is the reverse osmosis membrane is also called almost a non porous membrane. So, therefore, the transport mechanism is dissolution, diffusion and desorption, and it is basically depending on the operating pressure range. What is the throughput of the process will be depending on the operating pressure range. Typical operating pressure range will be above 25 atmosphere. So, in most of the plants, desalination plants, they operate around 50 atmosphere, 60 atmosphere, because one has to overcome the osmotic pressure of the solution in order to get the first drop of water out of the reverse osmosis membrane. More be the operating pressure, more gradient will be created, and one will be maintaining an effective driving force. That is the operating pressure minus the osmotic pressure. So, that will be more. If that will be more, the throughput of this process will be more, and it will be commercially viable, it will be more viable commercially. So, what are the various applications of reverse osmosis? First application, as I told, for the desalination purpose, and it has been used quite widely in Middle East, in other countries as well, to produce the potable water from saline water. Then other purposes, for example, separation of smaller sized solutes and salts from any process streams. What is nanofiltration? Nanofiltration is basically a process in between reverse osmosis and ultrafiltration. Typical pore size of the nanofiltration membrane lying in between 10 angstrom to 20 angstrom. And we are talking of a very good nanofiltration membrane leads to separation of monovalent salt between 40 to 80%, okay, and divalent salts quite high, (60 to 90% or even higher). Then all the molecular weights that will be all the solutes having the molecular weights in the range of 150 to 1000 Dalton, they can be separated by the nanofiltration membrane. In fact, there will be grades of nanofiltration. There are various cutoffs of nanofiltration membranes are available, can be fabricated, which will be separating various solutes which will be having the different molecular weights. Now, all the dyes they have the we are encountering for textile industry and other purposes, industrial purposes, they have the molecular weight in the range of 150 to 950 Dalton. All the polyphenols from plant extract, they will be having a molecular weight between 300 to 800 Dalton. Steviosides, like there are various specialty phytochemicals obtained from the plant. For example, stevioside, rubidoside, they will be having a molecular weight in the range of 700 to 900 Dalton. So, all these solutes can be separated or can be concentrated for the nanofiltration. In fact, if you remember that membrane based processes can be used either for purification, concentration, separation, and even fractionation, if you select a proper membrane and fix your objective, what type of operation you would like to carry out. So, therefore, in case of nanofiltration, the operating pressure drop will be less, and the transport mechanism is same as permeation, like reverse osmosis, because its pore size is slightly larger than the reverse osmosis. The transport mechanism is permeation, and operating pressure drop will be slightly less than reverse osmosis, and typically it will be in the range of 10 to 20, 25 atmosphere. And what are the applications? As has been discussed, the applications will be separation of dyes, polyphenols, lower molecular weight, protein, polymer. It has a wide application in the pharmaceutical industries. So, nanofiltration can be used for the fractionation, even for the concentration, and even for the fractionation. So, that goes for the nanofiltration. Then the it can be used for the water softening, because the divalent salts, calcium, magnesium, iron can be removed by the nanofiltration operation, and nanofiltration is also used as a pre-treatment, sometimes to pre-treatment as a pre-treatment of reverse osmosis system, so that some amount of salt is removed by the nanofiltration and load on reverse osmosis is reduced. It is also used to produce the process water for an industrial plant, because in any plant, if you use saline water for the as an utility stream, then that will cause the corrosion of the pipelines. So, one can use nanofiltration for softening to remove the salts and calcium, magnesium, so that the deposition and scaling of the pipelines can be reduced. So, nanofiltration has quite different applications. Then we will come to the categorization of ultrafiltration. The ultrafiltration has the versatile capacity membrane. So, it has a pore size distribution, pore size range in the range of, let us say, 20 angstrom to 1000 angstrom, and it has the solutes that can be separated as a molecular weight in the range of 1000 to even several lakhs, maybe 5 lakhs, 1000 Dalton to 5 lakhs Dalton. Okay. So, bigger size particles can be separated by the ultrafiltration membrane, and the operating pressure requirement is less, and it will be in the range of 3 to 8 atmosphere. And typical applications, and it is a huge applications, because this takes care of solutes, separation of solutes of a wide range of applications. So, separation of proteins, separation of polymers, polysaccharides like pectins in clarification of fruit juice. There are various applications of ultrafiltration, and the mechanism of transport it is a mixture of diffusion and convection. For lower cutoff membranes, where we will be separating the solutes which will be having low molecular weight. For open membrane, open ultrafiltration membranes, mainly the convection is the governing mechanism. Okay. So, that goes for the ultrafiltration. The final membrane based process is microfiltration, that we will be talking about. In case of microfiltration, we are really talking about a porous membrane which will be having a size more than pore size in the range of microns, 0.1 micron to and higher. And molecular weight of solutes that needs to be separated will be high, maybe more larger size molecules, micron sized. Solutes are separated by microfiltration, and the pressure requirement will be less, 1 to 4 atmosphere. And what are the various applications? Applications are separation of clay, paint, very high molecular weight solutes. And then microorganisms, they fall in under category microorganisms like bacteria. Typically, all the waterborne bacteria can be separated by the microfiltration processes, but the virus, they will be having a lower size. One has to go for an ultrafiltration membrane to remove the virus from the aqueous solution. So, what is the transport mechanism? transport mechanism is mainly convection. Okay. So, these are the four major categories of membrane based separation process. Now, we will be looking into the various properties and definitions which will be coming across quite often in this course in order to model the modeling and simulation of the process. So, will be the first property that will be looking into the osmotic pressure of a solution. What is the osmotic pressure of a solution? Every osmotic pressure of a solution indicates the thirst of water. So, a solution more osmotic pressure means the solution is more thirsty for water. So, let us conduct an experiment. Suppose we will be having a two chamber system separated by a semi permeable barrier, semi permeable membrane. Semi permeable membrane means it will be open to a particular species and it does not allow to transport any other species. For example, if you have a salt and aqueous solution of salt, that means there are two species in this system, one is the salt, another is the water. So, water being smaller in size, this perfectly semi permeable membrane will allow water to permeate through it, and it does not allow salt to permeate through it. So, therefore, let us keep one chamber to be filled up by water, that is a solvent, and we fill the other chamber by, let us say, NaCl solution. So, NaCl is a solute. Now, this membrane allows water to permeate through from the solvent side to the solution side. So, it is basically the solution side and this is the solvent side. So, as time progresses, the water concentration or activity of water is less in the solution side. So, since this membrane is a perfectly semi permeable membrane, it allows only water to permeate through it from the solvent to the solution side. So, therefore, the water being transported from this side to this side, and this will be kept on going unless an equilibrium will be reached, and that typically that equilibrium will be reached around it will take around 24 to 36 hours. So, at the equilibrium what happens? The level of water comes down in the solvent side, and in the same time the level of water in the solution side goes up. So, therefore, it will be creating a hydrostatic pressure of rho g h, where h is the final height difference of the level of solution in both the chambers. So, this rho g h or the static pressure that will be created by this system is known as the osmotic pressure. Osmotic pressure of solution. Now, this osmotic pressure will be very important. So, if we now let us look into the another system where we have a higher concentration of salt in the solution side. If we have a higher concentration of salt in the solution side, the water activity will be very less in the solution side, and therefore, more water will be coming from the solvent side to the solution side in order to attain the equilibrium. So, therefore, the after equilibrium, the height of the solution side will be more compared to the height of the water solvents of water in the solvent side. So, the height difference will be more in this case, and the osmotic pressure will be more. So, the conclusion is, if NaCl concentration goes up, the osmotic pressure development will be more. Therefore, osmotic pressure is known as a colligative property. And it is directly proportional to concentration of solute. So, osmotic pressure is typically denoted by a symbol pi, and pi is proportional to C. Another property of osmotic pressure is that osmotic pressure is inversely proportional to the molecular weight. Okay. So, if we are talking about the molecular of a smaller solute which will be having a molecular, in fact size of the solute is directly proportional to the molecular weight. So, if we have a smaller solute that which will be having a smaller molecular weight, its osmotic pressure is high. So, therefore, one can have high osmotic pressure under which situation? If we have a smaller molecular weight solute and larger concentration of the solute. Typically, in a sea water, the concentration of salt is around 20,000 to 30,000 ppm. That is 20 to 30 grams per liter or kg per meter cube. And what is the molecular weight of salt? It will be having very less. Its molecular weight is around 59 Dalton, 58.5 to be precise. So, it will be having the salt. So, therefore, at this concentration of salt, sodium chloride at a with a molecular weight around 58.5 Dalton, its osmotic pressure will be very, very high. If you really calculate, the osmotic pressure turns out to be around 20 to 22 atmosphere. So, therefore, in order to get the reasonable throughput through the process or system, one has to have an operating pressure which will be higher than the osmotic pressure, which will overcome this osmotic pressure. So, therefore, 25 atmosphere and more is prescribed as the operating pressure of the reverse osmosis system. Now you must have understood that osmotic pressure, if you go for higher molecular solutes, the osmotic pressure will be less, because it is inversely proportional to the molecular weight of the solutes. Therefore, for higher molecular solutes, the osmotic pressure is less. So, therefore, the operating pressure requirement will be less. So, that is why if you have observed, when you have defined the various categories of membrane based processes, as the pore size of the membrane increases, the pressure requirement decreases. So, this is the reason, as the pressure requirement is as the pore size of the membrane is increasing, we are really talking about separation of solutes which will be having the higher sized or which will be having the higher molecular weights. So, their osmotic pressure is less. So, the operating pressure requirement for having a realizable throughput or which will be of significance, that will be the requirement of the pressure is less. So, for the microfiltration membrane, where we are talking about separation of very large particle, the osmotic pressure is negligible, and one can have very low pressure in the range of 1 to 2 atmosphere in order to get a realizable flux which will be commercially viable. So, the Van 't Hoff relation is generally used to quantify the osmotic pressure of a solution R T C by M. Okay. R is the absolute R is the universal gas constant, T is the temperature in absolute scale, C is the solute concentration, MW is the molecular weight. C is the solute concentration, T is the temperature of solution, R is the universal gas constant. Now, this is generally used for salts. For salts, this is slightly modified. There will be a factor that will be multiplied in front of this expression. This will be the valency of the strong electrolytes. If you are talking about sodium chloride, this will be Na plus and Cl minus. So, this factor will be 1 plus absolute of minus 1. So, it will be 2 RTC by MW. So, therefore, if you are talking about salts, this relationship, the linear relationship holds, and for concentrated for dilute solution of any macromolecules which is not salt, one can typically use the Van 't Hoff relation, which will be linear in nature. for example, dye and other material. But if it is you are talking about a concentrated solution of macromolecule, one will be using a polynomial of concentration. How this relationship is generated? This relationship is generated by conducting, by measuring the osmotic pressure of different concentration of solutes in an instrument called osmometer. If you use an osmometer and prepare different concentration of the solutes, one can measure the osmotic pressure, and then one has to plot pi by C versus concentration. In fact, this is very important how this relation or this correlation of osmotic pressure is generated, because we have to assume that the concentration for a pure solvent, the osmotic pressure is less or osmotic pressure is 0. So, if you talk about a concentration, if you talk about a pure solvent, C is 0 and osmotic pressure is 0. Therefore, whenever you are talking about the measurement of concentration, measurement of osmotic pressure of any solution, we measure pi as a function of C in an osmotic pressure, then prepare a table pi by C versus C, and typically this curve will be a polynomial through origin, and then this correlation will be fitted, and therefore, since there will be an intercept here, so therefore, there will be an intercept in this case. So, therefore, when we express pi as a function of concentration, it will be going through the origin. So, therefore, one will be getting a relation, confirming the relationship that for pure solvent, when the concentration is 0, solute concentration is 0, pi will be equal to 0. Okay. We stop here in this class. In the next class, we will be looking to the other properties and definitions, which will be very, very important throughout our course. Thank you very much.